All right, so this is another example problem. We have a man walking with some speed when he trips. And so we're supposed to estimate the angular velocity just after the impact. And the problem looks like this. So he's walking, his foot hits a small step. And we are given his mass moment of inertia about the ankle joint here. And we don't have to worry about this foot, and maybe we're neglecting anything that this changes. So he hits this, and then what happens? And you might not think that this is a conservation of angular momentum problem. I mean, it's certainly not a conservation of linear momentum, because there's going to be forces here in this direction and forces here. But if you neglect any of the ankle strength, because you don't want to be keeping your whole body upright just with the strength of the muscles at your ankles, if you neglect all of that and you assume that your ankle can't produce any torque here, and you assume that the weight, which is right above the ankle at this time, it's not going to increase the rate of falling, so because it doesn't provide any moment, then you can say at this instant angular momentum is conserved. So we can say, all right, let's think about what that looks like. Yeah, let's just move this paper out of the way, I guess. Here, so before the impact, the whole body is translating forward. We're just going to assume. And then after impact, it can't do that anymore. Now it has to rotate about this fixed point. And now the top of the body will be moving faster, and the bottom of the body will be fixed. So we can say that we can set those two equal together because there's no applied moments. And so now we're going to take this r crossed v for dm. And if we realize, oh, look, for the before case, the velocity is the same for every single r, which is really the heights here, then we will have v times the integral of r dm, which is just going to be the mass center in this direction, or the height. R bar, or the height, right? So that's where this actually is. So then on the other side, in the after case, we're going to have the same thing. We're going to have the moment of momentum, so r cross v dm, and then but now the velocity isn't constant for every point here. Now we have actually the velocity is omega times r. And so, and r is just whatever the distance is away from the point that we're rotating. So in this case, r is going to be up because we're neglecting anything that's happening in this direction. So now we're just going to have our omega r squared, take the integral of that. Oh, and that's actually I. So I about that ground point. Let's see here. And so then when you solve that, you can solve for omega by dividing this by I. And here I've plugged in the numbers, and you do in fact get this answer. All right, so let's see one more example problem. So now we're going to have some bar that's out in space, and we are going to impact it with some particle, and the particle hits it, and they want to know what's the final linear and angular velocity of the bar with its embedded particle. And the linear velocity is very easy. We're just going to conserve linear momentum in both directions. So the velocity of the bar times the mass of the bar plus the velocity of the bullet times the mass of the bullet before is going to be equal to the final velocity times the final mass. So this is m2 for the final mass. So the final mass is just going to be big M plus little m. So we can divide that, and we just have in the I direction the velocity of the big bar times the big mass over the combination, and in the J direction the velocity of the little mass times the mass of the little mass over the combination. And right, because they're originally going in this direction, originally going in this direction, so they'll be going a little slower than before in each direction. All right, but now angular momentum is conserved about the center of mass, but we need to know where is the center of mass on this. It's not going to be at the center of the bar, and it's not going to be right here where the particle is. It's going to be somewhere in between. So this is where this problem kind of we get some math, but we can just calculate where that center of mass is, x from the center here, by saying, okay, it's from the center, the bar would have 0 coordinate, and this would have 1/4 times m over the sum. Or we could similarly calculate the distance d from where the particle is embedded to the center of mass. If this is the center of mass and there's going to be some distance d, then we could have 1/4 minus x, L over 4 times minus x, and here we can solve this, and so and this should look pretty familiar. It's kind of the same as this, only now this is big M and this is little m. So you can get some expression for d, and now let's plug this in. So before, our angular momentum, only this particle contributes to the angular momentum about that center of mass. And this velocity doesn't contribute to the angular momentum about the center of mass, because if you took the cross product, it would be going in the same direction. So the cross product of Vm about the point, the distance between the center of mass and that's going to be 0. So it won't really be contributing. All we have is the slug, right? And that makes sense, because if the slug didn't hit anything, it wouldn't matter. So, okay, velocity of the big bar doesn't cause any moment. So here we're just going to have the original moment, original angular momentum is going to be that d here, which is going to be this distance between wherever the center of mass is and the particle, and times the velocity of the particle times the mass of the particle. And we have to set that equal to the new moment of inertia about the center of mass times the new omega. And this is actually what we're solving for. So now if we start substituting this stuff in, we're going to have this if we substitute d in here. And then we calculate this I bar by saying, okay, well, a regular for a bar about its center of mass is 1/12 ml squared. And now we have to add this distance here because of the parallel axis theorem. So we're going to have x of the center of mass. And so this is our, and we're squaring it, so that's this 1/4 becomes 1/16, and this m over m plus m, it becomes m squared over m, big M plus little m squared, and then we got our L squared and our m. And then the same thing over here, we're just going to have the particle squared times m. So we substitute all of that in, and then I did a bunch of this by hand. So now we can take that and try to start simplifying. You can see that the big M and the L, we can pull both of those out right away. And now we have little m times Vm, and we can put everything in terms of 12ths from 16ths. And then if you do that, then you can add all these top things together. And when you have this squared, you can expand that and then combine all these terms. And then, oh, look, how clever. This 4 and 7, if you add them up, they equal 11. So that's a hint that we can actually factor this into 4 big M plus 7 little m times big M plus little m. And so then that big M plus little m in the top will cancel out with the big M plus little m on the bottom. And then we can solve for omega. And if you look, then you can see that, yes, indeed, you do get the same answer as we know we should get for the angular velocity of the bar after the particle is embedded.